honestly think everybody in here has heard the majority of this information before, but we're just going to hit it so we're all on the same page, and it'll be a nice review for the metric system. Yes?
And you said all these are uploaded to Blackboard?
Yes.
Right? So
Correct. All of these are already uploaded to Blackboard, so you don't have to write everything down if you don't want to. You could just write down the examples or the addition or whatever. Okay, so the metric system and scientific notation. So first of all, let's talk about the English system. That's what we use. That was the first system that people used in the first place. There's only 3 countries that still use this system, and that is Burma, Liberia, and of course us. We're not with the current times. Most units have been passed down with various definitions. So like for instance, the inch. The inch used to be defined as the distance between your knuckle to the tip of your finger. That's what people that's how they defined an inch back BC, long time ago. So they didn't have instruments. They weren't able to measure using a ruler. They didn't have a ruler. So they used pieces of their bodies or common objects to measure. Another example was a cubit. This was the distance from your elbow to the end of your middle finger, which is approximately now 18 inches. And another example is the foot. The foot is named for, they used to actually use the length of your foot. They actually used the foot of a king, but now once he died, they just used the average man's foot. But everybody's feet are different sizes, so then they kind of expanded it to mean 4 palms or 16 fingers or 36 barley corns. So basically, the English system uses oddball ways to measure. Okay, it wasn't defined like the metric system. It was just kind of whatever they had laying around. Because again, like I said, they didn't have a ruler. They didn't have these things. So they just used what they had. And then the only bad thing about this is, do you think everybody's arm's the same length? Or everybody's foot's the same length? So on and so forth. Or do you you guys know how much 36 barleys of corn is? That's actually the corn taken out of the middle of a husk. So if you took 36 of those and you put them side to side to side, that's what a foot is. So now we don't even know what these terms are. Maybe back then they did, but now we don't even know what some of these terms are. So some of the reasons that this system is bad is the terms depend on where you were in the world. It depended on who was defining it. It depended on how big you were. It depended on what items you had in your household. They were not consistent. Plus, like I said, it was dependent on where you were in the world. The English system also contains a lot of units, a lot of various units that have different definitions, that have different amounts. So like for instance, the English system, for volume, we have the cup, we have pint, we have quart, we have a pottle, which most of you have never heard of before. We have a gallon, we have a peck, and we have a bushel, and it goes on and on and on and on and on. Some of those we've heard before, but some of them, I'd never heard of a pottle until I made this PowerPoint. Have been thrown out because they weren't useful. We all use cups pretty often, and we use gallons pretty often, but even when it comes to pint and quarts, we still don't even use those very often. I still have to Google the conversion factors because I don't use those very often. And then we also have added a few. We also have added things like the fluid ounce. That's what your beverage is. If you look on your water bottles or your tea bottles or whatever, it is listed in fluid ounces, even though ounce is usually a way to measure weight. And then they also added the tablespoon and the teaspoon, and that's what we use for baking needs, right? Just let me know if I go too fast for anybody. Sometimes I start talking fast. Another downfall to the English system is it's really hard to move between units because oftentimes there's not an easy conversion factor, and every conversion factor is different. Like for instance, there is 12 inches in a foot, but there's 3 feet in a yard, and so the numbers are always different. Or there's 60 seconds in a minute, and there's 60 minutes in an hour, but there's 24 hours in the day, and then there's 36 days in the year. So every conversion factor you have to memorize is a different number. And so it's like a series of memorizing as opposed to one consistent way. So like for instance, if a recipe calls for 2 teaspoons of salt and it makes enough for 4 people, how many teaspoons would you need to make enough for 100 people? Well, that would be 200 teaspoons. And I don't know about you guys, but I don't really want to stand in the kitchen and measure out 200 teaspoons of salt. So most of you, or what I would do is I would try to Google the conversion from teaspoons to cup, because cups is a lot easier to measure out than it would be teaspoons. But again, the whole point of this is the English system is not very good to use because we don't know these conversion factors off the top of my head. I have no idea how many teaspoons are in a cup. I still don't know because I still didn't bother to Google it. But if I was trying to go from milliliters to liters, I could do that one in my head just because it's really easy to move between units in the metric system. Yet another negative to the English system is some units have multiple definitions. So like the ton is one example. We have a short ton, which is about 2,000 pounds, versus a long ton, which is 2,240 pounds. But most people just say ton. So it's like, which one are you talking about? Are you talking about the short ton or are you talking about the long ton? And so there can be some confusion there. Same thing with quarts. There's a liquid quart, there's a dry quart, and there's a British quart. There's 3 different versions of a quart. So even though we say quarts, which one are you talking about? Most of the time if we're talking about a quart, we're talking about a liquid quart, but you still need to make that distinction somehow. This is why the system has, for the majority, been abandoned. We're the only ones that really use it, and in a second we'll talk about we really don't technically use the true English system anymore. So let's switch gears now to the metric system. The metric system came around in the French Revolution times towards the end of the 18th century. It was actually in 1790, the French National Assembly asked the French Academy of Sciences to come up with some sort of system. By this point in time, this was when the printing press was developed. This is when we really started taking off. This is when books were being written. This is when the first science was really starting to come into play because people could communicate the results, and we were finally at a point where we could do this. And then it's hard to communicate results as if everybody's using the foot of different people, or if we're doing different sorts of measurements, it's hard to compare your results with another scientist, or even communicate with people on the street what you're doing if everybody's using different ways to measure. So they were kind of asked to come up with some sort of national way to measure that everybody would understand and would all be the same. Antoine Lavoisier was on this committee, and we're going to talk about him in a little bit. He's a very important chemist, and he came up with a lot of aspects to chemistry that we're going to study. So the metric system, the first one they came up with was the meter. This comes from the Greek word metron, or it means to measure, and this is defined as 1/10,000,000th of the distance from the North Pole to the equator. So that's what a meter is actually defined as. Another base unit for the metric system is the liter, and this is defined as 1 cubic decimeter. And then one unit, or the base unit for mass, is the gram, and this is defined as 1 cubic centimeter of water. And if you notice, the meter was the first one defined, but how did we define the other two? If you actually look at the definition, what did they use? They used meters. So basically the whole metric system is based off of what a meter is. We found ways to define volume and gram, etc., based on what the definition of a meter. So everything goes back to that basic definition. A meter is 1/10,000,000th of a distance from the North Pole to the equator. By 1870, this system was so popular in other countries that it was established as an international system, and they actually signed a treaty. It was signed by 17 countries, including the United States, even though we still technically haven't switched over to the metric system. We technically agreed that it was the best system to use just because it was so standard. And it is actually referred to as the SI system because, again, the French are who came up with this, and the French like to switch they don't say international system of units, they say system international. So they kind of switch their verbs when they speak. So that's why it's called the SI unit and not the IS system, which I'm sure will be a test question. Okay, I'll specifically put in the multiple choice, is it the SI system or the IS system, to see who remembers. Okay. Some items have also been improved, but for the most part, it remains the same. So over time, we've added units to it, but we have never changed the basic definition of what a meter is. All right, so like what I just said, the United States signed the treaty, but we never actually switched over to the metric system, or not officially. And we still technically use the English system. We call it a foot, we call it an inch, we call it a mile. We still technically use the English system. However, it's not the same English system from back then because we don't use our knuckle to determine what an inch is, do we? No, we use a ruler, correct? Well, in 1893, our English systems or our English units were defined by the metric system. So in the late 1800s, they said this 1 yard is going to be equal to 0.946 liters. So instead of using people's feet, so on and so forth, we're no longer doing that. We actually defined our English units using metric system. So we don't technically use the metric system, but we indirectly use the metric system because all of our units are based off of the metric system now. All right, so why is the metric system so much better than the English system? Well, basically because it uses the decimal system. Okay, we don't, like I said, when we're doing math in our units, we have to remember that there's 12 inches in a foot, and we have to remember there's 3 feet in a yard. So every time you try to convert, you have to multiply and divide by different numbers. Well, in the metric system, everything is represented by a base 10. There are 10 millimeters in a centimeter. There are 10 centimeters in a decimeter. There are 10 decimeters in a meter. There are 10 meters in a decameter. Everything is 10. So there's no memorizing because everything is based off of the prefix 10. And so basically what they did, instead of coming up with different names, like we go inch, foot, so on and so forth, instead of coming up with a different name for all the different types of meters, they just use prefixes. So it's no longer hard, and actually after you get good at it, you can just simply move the decimal back and forth. So I can just do it in my head by this point in time because I teach this all year round, every single day, all day long. So I can just do it in my head just because you memorize the prefixes and then you just move the decimal. So the prefixes that I'm talking about, you attach these to the base unit and they remain the same regardless of what the unit is. So once you remember the prefixes, all you have to do is plug in a different unit. And I am going to ask that you know these 6, so I would memorize these 6. They will be on your test. I'm trying to move so that there's not a glare right there. But the 6 main that I want you to know are kilo, hecto, deca, and then you have your base unit, so like meter or liter or gram or whatever. And then you have your decimeter, your centimeter, and your millimeter. My blinds are broken, or I would lower them. And if you notice off to the right side after the prefix, I have given the abbreviation. So like the abbreviation for kilo is a lowercase k, hecto is a lowercase h, and the lowercase is very important. So make sure that you write lowercase when needed and an uppercase when needed, although none of those have an uppercase. Okay, so the example I always like to do, I always like to throw an example so I can show you guys how to make these. If you can memorize the prefixes, you just plug in numbers. So if you guys remember back from high school, I'm sure your teacher taught you a mnemonic device to remember the prefix order. The one I teach my kids is King Henry died by drinking chocolate milk. And then and that way you can just put them in order straight down on your piece of paper. Again, it goes King Henry died by drinking chocolate milk. And then basically, I have kids do this on the side of their piece of paper every single time, but I can just see them write. And then what I tell them to do is I tell them to put a 1 by the base unit, and then you add a 0 to the left. So you go 10, you add 2 zeros, and then you add 3 zeros going up. And then you do the same thing, but in the opposite direction. So you add a 0 on the left side of the 1 as you go down. So then as you're trying to go between units and you're trying to do conversions, there's no sense in memorizing it if you can pick up on some sort of pattern. So like for instance, there are, I went the wrong way. See, I mess up sometimes. I'm sorry, I went the wrong way. You do the 0 on the other side as you go up. There we go. That looks better. So like for instance, there are 1,000 millimeters in 1 meter. And there is 0.0001 kilometers in 1 meter, so on and so forth. How many times did I mess up on one thing? So there you go. Sorry. It's right now, I promise. So for those of you writing it down. All right, so once you know the prefixes, you can use any metric unit. So I could throw in meters, I can throw in grams, I can throw in liters. It doesn't matter what the unit is. You can use the same prefixes for everything. And there are way more than 6 prefixes, but those are the only ones that we're really going to use in class. So those are the only ones I care if you memorize and can convert between. When a scientist needs a new unit to measure something, we are always developing new things. So like, did they have electricity back in the 1700s? No. So they had no need to measure the output of electricity. They had no reason to need the unit of an amp. But once we started coming up with electricity, they needed a new unit, so they defined the new unit as amp, and then they just used the same prefixes. So whenever a scientist needs a new unit, they define it, and then it fits right into the metric system. The list of prefixes and abbreviations can be found in your book on page 11. There's way more than just those 6. So if you're doing your homework, like there are a few homework questions that I'm going to give you, or occasionally in a lab, if you're given a prefix that isn't one of those 6, just turn to page 11 and it'll give you the conversion factor. And then again, the important thing is to pay attention to capitalization. So like for instance, 1 milligram, 1 lowercase mg, is equal to 0.001 grams. However, if you accidentally capitalize that m and you put 1 capital mg, that doesn't mean milligram, that means megagram. So we're actually talking about 1 million grams. So make sure that you capitalize in lowercase where appropriate. Really wish the sun would go down. All right, so another thing that we need to talk about a little bit is temperature. Materials expand and contract when heated or cooled. Usually, so volume usually depends on what temperature. And usually, when you expand when you're heated and you contract when you're cold, that's why at winter or in the summertime, your doors in your house, your wooden doors won't shut as well. They kind of stick. That's why, because the wood expands as it gets hotter. In the wintertime, that's not a problem anymore. If anything, you probably have a bigger gap between your door and the sill than you normally would, because things expand in the heat and they cool in the winter. The only thing that doesn't really follow this is water. It contracts, it gets smaller and smaller and smaller until 4 degrees Celsius, and then at 4 degrees Celsius it actually starts to expand, and that's why in the wintertime you get cracks in your driveway or cracks in the sidewalk, or if you have a crack in your windshield, and it'll crack and maybe make the crack even bigger, because as water gets in there and it freezes, it actually expands. You guys all know this, you know ice expands in an ice tray in the freezer, right? And then, you can't see it, but down at the bottom, in here, we know Fahrenheit. On the news, they tell you the temperature in Fahrenheit. But we're not going to use Fahrenheit. We're going to use Celsius. So you might have to do a little bit of converting back and forth. We're going to use temperatures or thermometers that do in Celsius. So just make sure that you write the degree down in Celsius, and then you don't have to do any conversions. But just in case, to go from Celsius, it's kind of a funky calculation. That's why it's always hard to remember. You take 5/9 times your degrees Fahrenheit minus 32. And then to go from Fahrenheit, or to go, if you have Celsius and you want to go back to Fahrenheit, you take degrees Celsius, you add it to 32, and then you times it by 9/5. So they're kind of weird calculations. Can everybody see it? I really make myself so big.
Degrees Celsius plus 32. If I don't have to take notes, I don't remember.
You didn't take notes mostly anyway. All right, so this is starting just a little bit of math. It's easy math though, but we need to be able to go between units. We need to be able to convert, and there's several ways where we can convert. I'm going to show you the math way, and then I'm going to show you the move the decimal way. So whichever way you like, you're more than welcome to use. I don't care. I have no preference. As long as you get the right answer and I can see some sort of thought process, you're going to be good. So to go from one unit to the next, so like for instance, to go from meters to kilometers, should you multiply? Should you divide? What do you multiply by? What do you divide by? So on and so forth. So, for instance, if you go from a larger to a smaller unit, you're going to actually be multiplying. If you're going from a smaller to a larger unit, you're going to divide. But that's hard for me to remember. I actually had to sit down and think about it when I was making these notes. I do dimensional analysis, which is a big word for something that's really easy. Basically, what you do is you take conversion factors and you make them into fractions. We all know what fractions are. We all know how to make fractions, and so it's something that you already know how to do. And it's always equal to 1. So a conversion factor is always equal to 1. So like for instance, 1 meter and 100 centimeters are the exact same thing. 1 meter, 100 centimeters are the exact same quantity of length. You're using a different unit technically. You're using a different measuring stick, but they're going to be the same amount. So that would be a good conversion factor. Okay, what you do is you have to figure out what unit you want to convert to, and you have to figure out what unit you're currently in. So if you're in meters and you want to go to centimeters, then you put what you want on top of the fraction, and you put what you're currently in on the bottom of the fraction. So I always say you put what you want over what you have. So let's do an example. So like for instance, if we are trying to convert 2.3 meters to centimeters, what I always say to do is you always start off by writing down what the problem's giving you. So the problem's giving you 2.3 meters. And then where are you going to? So we're going to centimeters. So we need a conversion factor that goes from centimeters to meters. And this is where the thing that I've written over there on the board comes in handy. If you have this memorized, if you can write this down really quickly, then it's going to help you come up with this conversion factor. So all I do is I look over there and I see, okay, what number is next to the base unit? That's a 1, so that's where I got the denominator. And then I look back up there and I say, what number's next to the centimeter? And I see 100, so that's where I got the numerator. And then I put it in a fraction. I put what I wanted over what I had. I wanted to convert to centimeters. I was currently in meters. That way this unit and this unit cancel out. We're left with centimeters. That's what we want. And then all we have to do is plug it into our calculator. That way you're never going to be accidentally multiplying when you're supposed to be dividing, or accidentally dividing when you're supposed to be multiplying. Or sometimes the metric system is nice because everything's in a base of 10, but sometimes it's hard to go straight from kilometers to millimeters. Sometimes it's hard to come up with those conversion factors in your head. So sometimes you might do more than one step, but this is just one way to kind of take out the silly mistakes you could possibly make. Another example, if we are trying to convert 5,380 centimeters to meters, again, what we do is we write down the number that was given to us in the problem. So they gave us 5,380 centimeters. I put what I want over what I had. I want meters. I had centimeters. And I actually write the units down, and then I look up the numbers. If I look at the board, the number next to the meters was a 1. The number next to the centimeter is 100. This unit cancels out that unit. We're left with the meters. And then you just do the math in your head on the calculator, however you like to do math, and you get an answer of 53.8. So what did I honestly do there? Did I have to put this in my calculator? What did I do? I just moved the decimal, didn't I? Moved the decimal over twice. All right, so if you notice, in the first example, I use this conversion factor. In the second example, I use this conversion factor. But aren't they the same conversion factor? They're both equal to 1, and they're the exact same numbers, except this time I was going to a smaller unit. And in this example, I was going to a bigger unit, so you just flipped the conversion factor. All right. Sometimes, like I said, you have a little bit more complicated. Some of these are really easy. Some of them are a little bit more complicated. And you might need to do this in 2 steps. So, like, for instance, how many centimeters are in 1.3 kilometers? It's kind of hard for me to go straight from one to the other. I don't like to go through the base unit. I like to go to the base unit and then to the next unit, just because a lot of people make silly mistakes there, because in our head it's hard for us to multiply by 0.01. It's a lot easier for us to use the big numbers. So in this case, I would have done 2 conversion factors. So I wrote down what I started with. The problem was asking me to convert 1.3 kilometers. So like I said, I like to go to my base unit first. It just helps keep you from making silly math mistakes. So I put what I want over what I had. I wanted meters. I was in kilometers. That way my units cancel out. Then I look over at the board. I see that there is a 1,000, well, not quite. There's 1,000 meters in 1 kilometer. Again, I don't like using 0.001 because I can't do that math in my head. I would much rather multiply by 1,000 because then you just add 3 zeros. So you can put that 1 over there on the board. You see where I put the 1 with the base unit? You can put the 1 wherever you want. As you go down, you add zeros to the right. As you go up, you add zeros to the left. So that 1 can go wherever you want it to go. So now I'm in meters, but the question's not asking for meters. It wants centimeters. So then I need another conversion factor, the second conversion factor, to make the meters cancel out. I put the meters on the bottom, put centimeters on the top. This unit cancels out. We're left with centimeters, and then I just have to do the math. So I multiply by 1,000, then I multiply again by 100, which is how many zeros? 5. So then I just add 5 zeros onto the end, which technically only 4 because there is a decimal already. Remove the decimal place over 5 times. All right, so you guys are quiet. All right, so as you become better with this, you'll get that memorized. After you do your homework, you'll have those 6 prefixes memorized and you'll probably be fine. But you'll honestly learn how to just move the decimal in your head. So the first way I was going to tell you was the dimensional analysis. It's actually the harder way, but if you don't know your prefixes already, that's the way to do it. Once you have them memorized, it's really easy to just move the decimal. So basically, you think of that as a ladder. So you think of the prefixes like a ladder, and I'm actually going to rewrite them just a little bit for you. So instead of writing them straight up and down, write them at a diagonal. And you think of it as a ladder. So like, for instance, if I'm starting with kilo and I'm wanting to go to centi, I move 1, 2, 3, 4, 5 times, and I went to the right, didn't I? So you're going to move your decimal to the right 5 times. So like, for instance, if we start with 1.8, you're going to move your decimal 1, 2, 3, 4, 5 times. Add zeros. And then no conversion factors needed. It happens the exact other way. So like, for instance, I can't see my example, so I'm just going to make up one now. If we are starting with deci and we're moving to hecto, we're going to move 1, 2, 3 times to the left. So if we start with 1.8 again, we're just going to move it 1, 2, 3 times, add the zeros, so that's how many hectometers we have. So again, once you memorize the prefixes, all you have to do is move the decimal, and then your math gets really easy. Alright, so now we're going to talk about scientific notation for just a little bit. This is the method for writing really, really, really big numbers or really, really, really small numbers without all the zeros. So like, for instance, you wouldn't want to write 1 billion trillion. I mean, that would be a lot of zeros. And more importantly, you can't put that in your calculator. So in science, specifically chemistry, we're actually going to be dealing with really small numbers a lot when we talk about the atom. When we're talking about the size of an atom, when we're talking about the size of the things that make up an atom, we're going to be talking about really small distances. And so putting all of those zeros after the decimal place before your first significant number can be kind of gruesome. Plus, the whole point of knowing the distances so that you can do some math with them. If we can't put them in our calculator, then what's the point? So we had to come up with a way to communicate really big numbers and really, really small numbers. So basically, it is based on the use of exponents. Based on the use of exponents and the number 10. So basically, you take 10 and you raise it to a positive number, and I just called it n. Tens are being multiplied together. So if you have 10 to the 6th, you're multiplying 6 tens together, or you're adding 6 zeros. So as opposed to adding all those zeros after the fact, you're just going to write times 10 to the 6th. Saves you time when you're writing. It saves you time when you're putting things into the calculator. Just makes everything a little bit easier. Like 10 times 10 to the 4th would be like multiplying 10 or 4 tens together. So it'd be like 10,000. Each increase of 1 power makes it 10 times bigger. And so, again, if you have times 10 to the 5th, you're honestly just adding 5 zeros. Positive exponents represent really, really, really big numbers. So if you have times 10 to the 23rd, you have 23 zeros added to after the number, so that's a really big number. However, we need a way to represent really, really, really small numbers. So what we do is we actually just make it a negative number. It doesn't mean that it has a negative value. It's just that negative is a way to tell you that we're dealing with really small numbers. So times 10 to the 0 means that the 1 is followed by no zero. So if I say 6 times 10 to the 0 power, I'm just talking about 6. Okay? If you say times 10 to the negative 3rd, you need to add zeros onto the left side this time. And the negative exponent isn't as easy to remember as the positive exponent, because if you have times 10 to the 6, you add 6 zeros. But when you have times 10 to the negative 6, you're actually adding 5 zeros to the left. So it's a little bit harder to remember, but I always just remembered it as 1 less. So times 10 to the negative 7th, you're adding 6 zeros. Times 10 to the negative 47th, you're adding 46 zeros to the left. Okay. All right, so let's actually just do this. When you are writing scientific notation, what you want to do is you want to move your decimal to where there is only one number to the left. So you don't want it to be 10.8, you want it to be 1.08. You want to move the decimal so there's only one digit. Then what you do is you count the number of times you moved the decimal, and then you need to determine the sign of the exponent. So let's just do an example. Let's do a really big number. Let's do 43. This we can't put on our calculator because the calculator usually only has 9 digits, and this one has 10 digits, so we wouldn't be able to put this one in the calculator. So the first thing says move the decimal so that there is one non-zero digit to the left. So we all know that in a big number like this, there's an imaginary decimal right here, correct? So we want to move it to right here. So now we have 4.3. But then I need to count how many times I move the decimal. So I'm going to count it as 1, 2, 3, 4, 5, 6, 7, 8, 9. I write times 10. The 9 goes right there. And then I need to determine if it's positive or negative. Remember, really big numbers get positive exponents. Really small numbers get negative. So is this going to be positive or negative? Positive. And then so if we were dealing with meters, this is the same thing as this, except this you can put in your calculator, and this one you can't. Okay, so let's do an example going the opposite way. So let's do so first of all, we see my decimals right here, but we want to move the decimal so there's one digit to the left. So where should I put my decimal? After the 1. Some people want to put it right here just because when you move this direction, you move as far over as you can, but you want to move it to where there's only one digit, and then you need to count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I moved it 11 times. So now I just need to rewrite it. What do you think I'm going to rewrite it as? 1.07. Then what am I going to write?
Times 10.
Negative 11th. Why is it negative this go around? Because it's a really small number. This is not telling you that the number itself is negative. That is its signal that this is a really small number. All right, so let's see if we can do these. Can somebody walk me through these two examples? Because I know how to do it. So how should I do that first one? What do you think I should do? I need to move the decimal. Where is the decimal to start off with?
The 0.
It's behind the 0. Where do I need to put it?
In between the 9 and the 3.
In between the 9 and the 3. And then I just count and rewrite the format, correct? So my new number is going to be 9.3 times 10. And now I count. I'm going to move it 1, 2, 3, 4, 5, 6, 7. Is it going to be positive or negative? Positive. Okay, so what about this one? Where do I even start? What's my first thing I should do? Move the decimal to where? Between the 1 and the 5. So I'll just go ahead and write down my format. 1.5 times 10. Then I count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Positive or negative? Negative. And don't forget your unit, but for right now, I didn't give you one with units. Okay, I'm going to try to get my blinds down so you guys can see this.
Did you just break that?
I did. Fixed it, kind of. Okay, now, when I will teach you guys how to do these in your calculator, scientific notation. If you ever, if we don't need to do it, I'm not going to waste my time and teach you guys how, because it's actually a little bit complicated. But if we ever get to a calculation or we need to do this in our calculator, I'll show you guys how to do it. But your calculator often likes to spit it out like this. It'll spit it out as 3.2 little 3. And so this is what people write down, or this is what people think it is. 3.2 to the exponent 3 is actually saying 3.2 times 3.2 times 3.2, which is not exactly scientific notation, right? We need to write it as 3.2 times 10 to the third, because what we're actually doing is we're taking 3.2 times 10 times 10 times 10. So this and this are two completely different things, and you're going to get two completely different answers. So whenever we try to put this in our calculator, a lot of people try to put it in like this, because that's how the calculator tells you it looks like. But just make sure that you're writing it in the format, and then when we get to the calculations, I'll show you how to put it in a calculator so that you're doing it correctly. But this is a very common mistake that people make when they're doing calculations. So, all right. So you guys have a little bit of homework. It's just 6 questions. It's on page 19 and 20. It's at the very end of chapter 1. How I feel about homework is you guys are in college. I'm not going to make you do your homework. You guys are big kids now. If you don't want to do it, don't do it. Okay? On Thursday, I'm going to go over it. So I'm going to answer questions. I'm going to tell you what the right answers are. I'm going to do example problems. So it's kind of like you can do it and you can put forth the effort, because when it comes to tests, I kind of like to copy and paste off the homework. So if you've already done the homework problems, then studying for your test is going to be really easy. If you wait till the night before and try to do all of your homework problems, it's going to be a lot of questions to do, because there's probably about 10 questions every homework, and then times that by 3 weeks, that becomes 60, 70 questions. So,
It's in this book, right?
yes, it's in that book. All right.